So in this video, we're going to use linear systems to solve a chemical equation. Okay, so we have a chemical equation up on the board for photosynthesis. Photosynthesis takes water and carbon dioxide and turns it into sugar and oxygen gas, right? So how do we convert this chemical equation to a linear system? Well, we use the fact that the matter is not created or destroyed, and it just changes from one form to another. So we have to make sure that we have the same number of atoms on both sides of the chemical equation. So if we want to balance the hydrogens, we have to have that 2x is equal to what? How many hydrogens on this side? 12z. Okay. To balance the oxygens, we have x plus 2y is equal to 6z plus 2w. All right, now the oxygens are balanced. So let me just write this up here. We have the hydrogens we're balancing, we have the oxygens we're balancing, and now we have the carbons which we wish to balance. So to balance the carbon, we have y is equal to 6z. Okay? Y is equal to 6z, and that's it. Okay. So what we have is, a linear system. I'll put it into a more organized format for the purposes of converting to an augmented matrix. All right, so here's the linear system. We have 2x. We move the z to the other side, so we have minus 12z, and no w's is equal to 0. Then we have x plus 2y minus 6z minus 2w is equal to 0. And we finally have y minus 6z is equal to 0. Equals 0. Okay, so this is nicely formatted so we can create the augmented matrix. Doing so, let me erase this half of the board here. Okay, we have what? We have 2, 0, negative 12, 0, and then a line with zeros, right? So 2 there. So we have, for the next equation, translated into rows, we have 1, we have 2 minus 6 minus 2 equals, and it has a line with 0. And then for the third row, we have 0, 1, negative 6, 0, 0. So there we have our augmented matrix corresponding to the linear system. Okay? And now we're going to use row operations, which I've discussed in other videos, to convert this augmented matrix to reduced echelon form, and then we'll solve the ensuing linear system. So let's go to work here. So first thing that I'll do to get a leading 1 in the upper right hand corner is divide by 2. So I divide by 2, we have 1, 0, negative 6, 0, line 0. Is there anything else I can do? Well, yeah, there's other stuff I can do, but I'd rather do it step by step so you can see every step. 0, 1, negative 6, 0, 0. All right, so all I did was divide row 1 by 2. I guess I'll indicate that. Row 1 gets replaced with 1/2 of row 1. Okay? All right, now this leading 1 here can be used to get zeros elsewhere in the column. Notice that we have a 0 here, so the only number that I have to remove is this 1 in row 2. I'll do so by replacing row 2 with row 2 minus row 1. Okay, so that's what we're going to do next. I guess I'll draw the arrow the other way. Okay, so let's see what happens next. So row 1 remains intact. 1, 0, negative 6, 0, 0. All right, and then row 2 becomes 1 minus 1 is 0. 2 minus 0 is 2. Negative 6 minus a minus 6 is 0. Negative 2 minus 0 is negative 2, and we get a 0. All right, and row 3 stays intact because we didn't do anything with row 3. All right, so now we want a leading 1 in the next staircase position. So it looks like we can get that by dividing row 2 by 2, right? So row 2 gets replaced with 1/2 row 2. Okay, good. So we have 1, 0, -6, 0, 0. And then we have 0, 1, 0, -1, 0, and 0, 1, -6, 0, 0. All right, so we have a leading 1 in the next staircase position, which we'll use to remove the 1 in the column that it belongs to. All right, let's see if I have space here. I have space here. Row 3 gets replaced with row 3 minus row 2. Okay, so what do we have? We have row 1 stays intact, 0, 0. All right, row 2 stays intact, 0, 1, 0, -1, 0. But row 3 becomes 0 minus 0 is 0. 1 minus 1 is 0. -6 minus 0 is -6. And 0 minus a minus 1 is 1. And we get a 0. All right. So what's the next step? Well, the next step is we want another, we want the ones to staircase down. So the only option left to us is to divide by -6 to get a 1 here. But you know what? That's going to give me a fraction of 1/6. So, and I want to get rid of this 6 here. So conveniently, I can just take row 1 minus row 3. So let's do that. So row 1 is going to be replaced with row 1 minus row 3. Okay, and that's going to give us 1, because 1 minus 0 is 1. 0 minus 0 is 0. -6 minus a minus 6 is 0. And 0 minus 1 is -1. Okay, so you see we deal with row 1 without having to introduce the fractions. Row 2 stays intact, right? 0, -1, 0, and we have row 3, 0, 0, -6, 1, 0. All right, well, now we're forced to introduce fractions, but good thing we did that operation in row 1, because then we didn't have to subtract fractions and leave fractions in row 1. You know, it really doesn't matter. We're going to get the same solution otherwise, but, you know, it's cleaner and easier if we, you know, try to avoid fractions. Okay, so last step then, as I said, going forward, we'll take row 3 and replace it with -1/6 times row 3. All right, this yields what? 1, 0, 0, -1. Row 1 stays intact, all right? And then we have 0, 1, 0, -1, 0. And then we have 0, 0, 1, -1/6, 0. Okay, so you can see that we're in reduced row echelon form now. Our augmented matrix satisfies the conditions of row echelon form, the 1 staircase down. Whenever there's a leading 1, we have zeros elsewhere in that column. Okay, and we're good to go, right? Well, we're good to go where? We're good to go back to the land of equations, because what we're going to have is an equivalent linear system that will balance the chemical equation. Well, whose solution will balance the chemical equation? All right, let me not erase this one here. So what do we have? We have x minus w equals 0. Okay. Then we have y minus w equals 0. And we have z minus 1/6 w equals 0. So you see, this is a lot nicer linear system to deal with than the original linear system, you know, from the that was induced by the chemical equation. All right, so let's solve this linear system. To solve this linear system, we go from the bottom. So from the bottom, if this was a 4x4 system with a unique solution, we would see that W is equal to some number, right? But we don't have any information about W, so W is a free variable. So I'll write W, it's customary to write W is equal to T. Free variables are usually indicated by T, right? Now what do we have for Z? Well, we have Z is minus 1/6 W equals 0. Thus Z is equal to 1/6 W, right? Thus we have that Z then is equal to 1/6 T. Furthermore, we have Y is equal to T, and then we have X is equal to T. Y is equal to T, and X is equal to T. All right, so we have our provisional solution. Our solution to this chemical equation is thus S is equal to X is equal to T, right? It's an infinitely many points in four-dimensional space if you want to look at it mathematically. Y is equal to T, Z is equal to 1/6 T, and W is equal to T. And such that we would ordinarily say, if we're solving in just a 4x4 linear system that wasn't, applied to anything, we would say T is just equal to a real number. But in this case, we have T is going to represent the number of molecules, right? So it's okay for T to be 1, 2, 3, 4, 5, 6, etc. However, we have that Z is 1/6 T. Therefore, T must be a multiple of 6. So T is going to be equal to 6, 12, 18, etc. Right? So we can write that in mathematics is that 6 is equal to 12. Well, I don't want to say Z because that's negative numbers are out. So we can have 6n is a way to write this. Okay, in a more compact way. All right, but anyway, let's check it out. Let's see if this works, right? So for example, if T is equal to 6, that's our first value that's going to satisfy this chemical equation. And if T is equal to 6, does the chemical equation get solved? We hope so, right? So T is equal to 6, so we have 6 H2Os, right? And then we have Y is equal to 6 also, so we have 6 carbon dioxides, right? Now, if T is equal to 6, then Z is equal to 1. So we have 1 C6H12O6, and then we have W is equal to 6, so we have 6 O2s, right? Sorry, they're butting up against each other. So all we have to do is check this. So let's check the hydrogens. If we check the hydrogens, we have 12 on one side, that's good. And how many on the other side? We have 12 hydrogens on the other side. This is a 12, and this is an O6, right? Okay, so we have 12 hydrogens on the other side as well. Let's look at the oxygens. How many oxygens do we have on the left side? We have 6, right, plus 12. So we have 18. Hopefully there's 18 oxygens on the right-hand side. From here we get 6, from the sugar we get 6, and from the 6 oxygen gases we get 12. So voila, the oxygens balance as well. And let's see, what about the carbons? The carbons, we have 12 carbons. No, we have 6 carbons on the left-hand side, and we have 6 carbons on the right-hand side. And so the chemical equation balances. Now this technique, you really wouldn't use this technique to balance this chemical equation because, you can do that by inspection. But I wanted to show the method of using a linear system to do this because when we have a much bigger chemical equation, well, that's going to be harder to solve by inspection. Okay, good.